Welcome to Review Lecture number 8 in my online review course of Undergraduate Probability and Statistics. I'm Chris Mack, your professor for this class, and today we're going to talk about the expectation value and the variance, specifically for a discrete random variable. We'll apply expectation value and variance concepts to continuous random variables in the next lecture. First of all, what is an expectation value? Maybe you've heard of this term before, maybe not. If you haven't, don't expect it to be, pardon the pun, a brand new concept, because it's really just the mean. The expectation value is a very specific definition, but it turns out to be identical to the way we normally think about the mean of some distribution. For a discrete random variable, we characterize that variable by the probability mass function. As we talked about last time, the probability mass function, PMF, if we have a random variable, which I'll label as capital X, we always use capital letters for our random variables, then we'll do P subscript X to represent the PMF of the random variable X. And then it has a particular value at a number. Little x represents a number, 1, 6.2, whatever that number might be. And the PMF is simply the probability that the random variable x takes on that number. Now, one of the properties of the PMF is that the sum over all values of x for all the PMFs will equal 1. That's the normalization requirement of the three axioms of probability. Now we will define the expectation value of the random variable x as, we use the symbol capital E for expectation, square brackets, we always use square brackets to represent the expectation. The expectation of x is simply the weighted sum of all the x values, weighted by the PMF, the probability that the random variable will take on that value. So we see sum. Because it's discrete, we have individual values of x that could occur. It could be an infinite sample space, so it could be an infinite number of them, and this would just become an infinite sum if that were the case. But we simply take all the x values, multiply them by the probability that that x value will occur, and then add them all up. Let's take some examples. Let capital X be the sum of two six-sided fair dice. All right, we looked at this example last time where we showed what the PMF was. Here's a graph of it. The PMF of 2 is 136. That's the probability that you will get a sum of 2 when you roll 2 dice, sometimes called snake eyes if you play dice. The PMF of 3 is 236, etc., all the way up to the mode. The mode is the value that has the highest probability of occurrence, and the mode in this case is 7, and it has a probability of occurring of 1/6, and then higher numbers go down, etc. So if we want to calculate the expectation value, we will sum up all the values of k. I'll use k to be the sum of the 2 dice. Multiplied by the PMF of that value, so 136, 236, 336, etc. And we sum them all up for every value that could exist. Well, if you're curious as to what the answer is, if you carry out this summation, I think you could probably guess the answer is 7. The symmetry of this PMF would tell us that the mean must equal the median and the mode, which is 7. Let's look at a uniform distribution. If we have a random variable that follows a uniform distribution, and we have n discrete values, then the PMF of all values of x are 1 over n. So let's calculate the expectation value. The expectation value of the random variable x, the sum of over all x's of the value of x times the PMF. The value of x I'll call x sub I, and the PMF is 1 over n for every single x sub I. So I sum them all up from I equals 1 to n, since there's n discrete values, and what do we get? Well, we get an expectation value for a uniformly distributed random variable that is the arithmetic mean of all of the possible values. So I take all the possible values and calculate their mean. I get the expectation value for that variable. But we've looked at a number of different distributions that random variables can take on. Besides the uniform distribution, we also looked at the Bernoulli random variable. Remember, a Bernoulli random variable is a random variable that takes on a binary value of 1 or 0. The simplest example is a coin toss that produces a success with probability p. Of course, it doesn't have to really be coin tosses. We could ask, here is a nucleus, and it either undergoes decay, releasing an alpha particle, or radioactive decay, releasing an alpha particle, or it doesn't undergo radioactive decay. So it's a 1 or a 0, binary, success or failure. In this case, success simply being defined, it did undergo decay. And if you have some probability p, we can look at an individual atom and define a Bernoulli random variable like that. So here our random variable is defined as a 1 for a success or a 0 for a failure, and for the flip of a coin we'll simply arbitrarily define a head as being a success. The PMF, as we saw last time, PMF of 1 is equal to p, and the PMF of 0 is equal to 1 minus p. That's because we've defined our parameter p as the probability of getting a head, or a 1. Now, what is the expectation value? We simply work it out. In this case, the sum has over only 2 values. The sum of x times the PMF, I only have 2 values for x, it's 1 and 0. The PMF is p and 1 minus p. I carry out the sum, I get p. The expectation value is p for the flipping of a coin. This might be intuitive to you, but nonetheless, the math easily works out the answer. All right, we'll work some other examples of expectation in just a moment, but before we do, let's define another important concept about a distribution. It's variance. Now, we already know what a variance is. It's a measure of the spread of our distribution. But let me define it mathematically for the case of a discrete random variable. Again, a discrete random variable is characterized by its PMF, and we define the variance of a random variable as, well, first of all, I use the letters VAR of square bracket x to represent the function variance of x for my random variable, and it is the sum over all x values of x minus its expectation value, then that quantity squared, and we sum all those up weighted by the probability of achieving that particular x value. Hopefully this looks familiar with how we normally think about calculating variance for experimental data, for example. Obviously they're related. But here we apply as a weighting the PMF of whatever distribution our variable happens to follow. Let's take an example. Bernoulli random variable. Remember, a Bernoulli random variable is a succession of binomial random variables. So I toss a coin with a probability of getting a heads or a success of 1. I have the PMF of my Bernoulli random variable here, and then, as we saw before, the expectation is simply p. So we need to know that because we have to plug it into our variance formula. Let's plug it in. The variance only has 2 values. X values can be a p or 1 minus 1 or a 0 rather, and the expectation is p. So if I have 1 minus p, That's x equal to 1. I square that and multiply it by the PMF. Then I add it to the case of x equal to 0. 0 minus p quantity squared times the probability of getting a 0, which is 1 minus p. Sum that up. I get a variance, which is p times 1 minus p. Now maybe you thought that the expectation value equal to p was quite intuitive, but it's kind of hard to understand by intuition what the variance is going to be. P times 1 minus p is the variance. Notice that the variance is at its maximum when p equals 1/2. As p gets smaller or larger than 1/2, the variance goes down. At the extreme cases, if p is either 0 or 1, then the variance goes to 0. Does that make sense? Well, if p is 0 or p is 1, then there is complete certainty as to the result of the experiment. If you get a head with a probability of 1, well, you've got a two-headed coin, and you will always get a 1, and there's 0 variance in that result. Likewise, if I have a coin where both sides are tails, I will get a head with probability 0, and again the variance will be 0. So at least at the extremes, this seems to make sense. Now let's look at another distribution, the binomial distribution. Here we're going to repeat a Bernoulli trial n times. We'll have all of these trials completely independent, and the probability of a success p will remain constant for every trial. That's the definition of repeated Bernoulli trials. And we saw last lecture that the result, defining our random variable x as being the number of successes, the resulting PMF was a binomial distribution. What is the mean of this binomial distribution? What is the variance? Well, we simply apply our formulas. The expectation value of this random variable, the number of successes, is n times p. Does this make sense? If I have a single Bernoulli trial, I have the Bernoulli random variable, its expectation is p. If I repeat that Bernoulli trial n times, what would I expect? P is a constant, so I sum up all the expectations of every trial, I should get np. That makes intuitive sense. Likewise, the variance of the random variable x will be n times p times 1 minus p. You might recognize that the variance of a single Bernoulli trial is p times 1 minus p. And if I had n Bernoulli trials, what I'm saying is the variance is n times bigger. Well, this turns out to be a result of the fact that our trials are independent. And we'll talk about independence and how that impacts variance and expectation in a couple of slides. Let's go on to our geometric distribution. An example of the geometric distribution was I'm flipping a coin and I ask how many coin tosses are required until I get my first head or my first success. We define our random variable x as the number of tosses to get the first head. And we saw this as our PMF last time. Well, we go through the calculation using our formulas for the expectation and the variance. We find the expectation is 1 over p. Does that make intuitive sense? Well, if we get ahead with a probability of 0.5, then on average it takes 2 flips to come up with a head. I guess that does make sense. If the probability of getting a head is smaller, then on average it takes more flips before you come up with your first head. The variance, 1 minus p divided by p squared. The Poisson distribution. Recall that the Poisson distribution comes about when we let n, the number of Bernoulli trials, go to infinity while keeping n times p, the probability of success for a single trial, equal to a constant. That constant is the parameter of the Poisson distribution, and we saw the PMF looks like this. Hopefully you've seen a Poisson distribution in the past. It's quite common in many different physical applications. The expectation of a Poisson distribution is the parameter lambda, and the variance of the Poisson distribution is the parameter lambda. So this is kind of a unique quality of the Poisson distribution, that it has an expectation and a variance equal to each other. Lambda, by the way, is a dimensionless quantity. So that's why we're allowed to have expectation and variance identical, since the variance is a squared quantity, expectation linear in our random variable. Let me now, after going through a few different probability distributions for discrete random variables, let's talk about the concept of independence. We defined independence in terms of probabilities before, but let's see what the impact of independence is on expectation and variance. Before doing so, let me show you some general properties of expectation and variance for any two random variables, x and y. If I have any two random variables, whether they're independent or not, x and y, the expectation of their sum is the sum of their expectations. You can easily prove that. Since the definition of expectation is linear, we get this linear result. Likewise, if I take a random variable and I multiply it by a scalar and add a scalar to it, that is, I do a linear transformation on that random variable, I get a linear transformation of its expectation as well. So I simply multiply the expectation by a and add b. Variance, on the other hand, is a bit different. If I do a linear transformation of some random variable x and then take its variance, the offset b has no impact on the variance whatsoever. And a scaling factor, a, will scale the variance of x by a squared. Again, variance acts as a squaring operation, so any scaling of a results in a squaring of a and before scaling the variance. Now, let's look at some other properties of expectation and variance for the special case, when x and y are independent random variables. Now, this is important because many people make the mistake of assuming that two random variables will always be independent and then applying the rules that I'm about to show you in all cases. This is not true. There are many times when you can define two random variables, x and y, and they are not independent of each other. They have some interaction, in which case you cannot use the following two rules. Let me show you what they are. The expectation of the product of two independent random variables is the product of their expectations. If x and y are not independent, this will not be true. Likewise, and this is what many people mistakenly apply, even without proving that x and y are independent, the variance of x plus y, the variance of the sum of two independent random variables, is the sum of their variances. This can come in very handy, but only for the case when x and y are independent. Okay, well, we've defined expectation, we've defined variance to important quantities, to important summary statistics that we use on data, but also important quantities that we define for random variable distributions as well. Let's review what we have learned. As always, you should be able to quickly and easily answer these questions. If not, please go back and review the material again. What is the expectation value, and how is it calculated for a discrete random variable? What is the variance, and how is it calculated for a discrete random variable? What is the mean and the variance of the Bernoulli random variable and a binomially distributed random variable? And finally, what is the variance of the sum of two independent random variables, and how might that be different if my two random variables are not independent? Well, we've defined expectation and variance. We've define them for discrete random variables. Next time, we'll look at continuous random variables. Till then.